here has two peaks. Can you see that all that's happening is the wave is going up and then down. This one here has 4 nodes, and in particular has 3 peaks. Okay, and each one of these peaks is going up and down. It's beautiful, isn't it, right? What Hertz did was he made these standing waves by reflecting using parabolic mirrors, and he effectively calculated the wavelength. So what he did was, in particular, you have the original wave. So you have a source of waves, continuous waves being released. You'll have a normal wave passing through like this. Maybe I'll use this color this time. So you'll have a normal wave passing through like that. And what he did was, he reflected one of the waves that were coming off in this direction. Remember, waves go off in all directions. He reflected one of the waves that come off in this direction with the parabolic mirror. And as a result, by constructively interfering, and what happens with standing waves is that the point at which standing waves form are the points at which constructive interference occurs. So by looking at the points where, by having a spark gap at the end of the concave mirror that it was actually measuring, by moving the spark gap around, concave mirror, by moving the spark gap around, wherever the spark was the largest is wherever the standing waves occur. That is when you have an integer multiple of half wavelengths. So wherever the first one was, is basically half the wavelength. The second one is a full wavelength, and so on and so forth. So by using this technique, he calculated the wavelength.
Let's say there's 1 milliliter of solution in there. Okay? Now, what we don't understand is with the volumetric flask, it doesn't matter if 1 milliliter of water is in there. Okay? When we add in our solution, we'll add in say 10 mils of solution. This is a conical flask. This is the volumetric flask. Okay? We'll add in say 10 mils of solution. We're then going to pour in, how much is it? We have a 250 volumetric flask, we have 11 milliliters added in so far. So we want a total of, we want to add in another 239. Can you see how it doesn't matter if water's in there to start with? We're adding in more water anyway. We're going to dilute it anyway. Okay? And it doesn't matter if there's water in here to start with, because that's just going to help us dilute. Let's say if there was no water in here, then we need to add in 240 mils of water to make a total solution of 250. Okay? So any water that's remaining in there just means we don't have to add in less of we don't have to add in less deionized water to then make up a solution of 250 mils. Water that's already in there will just get incorporated into the solution. Now you're thinking, wait, well, that doesn't make any sense. How can we do that? Well, the fact is we accounted for the fact that there will be a total of 240 milliliters in there. We know our solution. We know how much, we know how much mass is dissolved in a beaker beforehand. We know that we added a certain amount of water in to help dissolve. We know that we then poured it in. We know that we're then going to add water to make it up to the mark. Okay? When we did this whole thing, we accounted for the fact that we would have a final 250 milliliter solution.
Okay, a shirt purchased at a 15% off sale cost. The purchaser $79.90. What was the original price of the shirt? So which means, let's say the original price is X, and then if you take 15% off X, which means you times it by, which means you only have to pay 75% of X, and that will give you 79.9. Do we know why we times it by 75% but not 15%? No matter, don't worry about that.
Oh, no, I'm saying no.
Yeah, the reason why is if you have X times it by 15%, you only get the discount, right? Right, you get the discount. So for example, if the original price is $10 and it says 10% off, then that would be, the discount would be $1, right? So this one you wouldn't want to use this one because we don't know the price of the discount. So you don't use this formula. So rather you use the other ones. So because you know what you paid for, this is the price you paid for, which is 75% of the original price is equal to that. That's why you use that. So we have x times 0.75 equal to 79.90, and then you're solving it for x have 79.90 over 0.75.
Yeah. That's 106.
106? Yeah, that sounds right.
This guy did a lot of experiments with the ultraviolet light and how it relates to the receiving loop. And by shining ultraviolet light onto it, he found that the spark intensity increased. And in particular, he put a piece of quartz in between the actual UV light and the receiving loop. And he found that spark intensity did not increase by simply putting a piece of quartz in between. What does quartz do with light?
Quartz
Yeah,
with light.
yeah. What does it do?
Isn't it given electrical?
Oh no. It disperses it, yeah. That's what it does. It basically doesn't allow it to go through easily. It pushes it off in different directions. That's why it's dull. Now, you put a piece of quartz in between the ultraviolet light and the receiving loop, and he still found that the spark intensity was exactly the same. So whatever was happening, the ultraviolet light was not being affected by the quartz, and that's what's still affecting the receiving loop. Now, after all this, he found that while he was experimenting, UV light shone onto the receiving loop, produced a more intense spark. He couldn't explain it, and he found that if he also blocked it with quartz, it still produced such an intense spark as well. He couldn't explain why this happened, but he now knows in hindsight that he actually discovered the ultraviolet effect, the photoelectric effect, okay? Which is the ability of photons, that is light particles, to eject electrons from the surface of the light. I mean, you guys all know what this stands for, right? Put two together and transform.
Now, what do you recognize this equation as?
X plus.
X squared plus y squared equal to 1. What does it look like? It's a circle.
Oh, it's a circle.
Yes. So this is what we call a unit circle. Because it's 1 unit. That's why it's a unit circle. Because the radius will be 1 unit. So let's say we have a point here. Let's call it x, y. And remember how we measure angle is always from the x-axis in the anti-clockwise direction. So let's have a look at this point. If we have, that would be the x-coordinates, and then this part would be the y-coordinates. Okay? So in other words, this will be x is equal to y. Can we see what is sine theta equal to? Sine theta is opposite over hypotenuse is 1 because that's the radius of the circle, which is 1. And what is the cos theta? Equal to x over 1, which is x. Now, can you see that the point x, y can be rewritten in terms of theta? Because we know that x is equal to cos theta and y is equal to sine theta. So we can rewrite our x and y coordinates in terms of theta.
Okay.
Okay? So which means x equals to y theta and y equals to sine theta. Okay? Now coming back to our unit circle equation. We will also substitute this into this unit circle. We have cos square theta plus sine square theta equal to 1. You see that? I'm just substituting my things. So, okay, so that's our first identity. Now keep in mind that when I write cos squared is equal to cos theta all squared. Okay, so note. They are the same thing, but generally in math we prefer this notation over this.